Power in a wave, we're not going to do a whole lot with power, but you will have at least one homework question about it. Power is how much energy. Remember, waves transfer energy, not particles. Power is how much energy is being transferred. And we'll have to go to the formula here. I don't know. Oh, there it is. There is the average power in a wave. The instantaneous power changes. So if I were to just like take the average of this graph, I would get 0 because some of it's positive. This is the absolute value of power we're looking at here. Because this bounces up and down, because our graph bounces up and down, if I were to just integrate over it, it would give a 0. So average power is the square of the amplitude and then square rooted. And it's just this formula. Like this is just a plug and chug. If somebody asked you about power, you just use this formula. What we normally measure though is intensity. So when you're at a concert and you want to know how loud is something, what you're talking about is how intense is the sound. And that's power per unit area that we then convert into a decibel scale. So intensity, you have some source of, say, sound here at the middle. That energy is going to spread out in an expanding sphere. If you want to know how loud it sounds out here at this position versus this position, what you're measuring is the intensity, which is power per unit area. Because our sound is expanding in a sphere, by area, we mean area of the surface area of that sphere. So our formula for intensity is power over area, or power over, you guys remember the formula for surface area of a sphere? 4 pi r squared, where r is your radius away. Okay, so our intensity, that's a function of r, is the power emitted at the source divided by the surface area of the sphere at that radius 4 pi r squared. That will come into play later when we talk about the decibel scale, which is a logarithmic scale of intensity. Is what if you have a string that's, say, attached at both ends, like on a guitar, and you let a wave go down and bounce back, and then go down and bounce back. And what if it bounces back and forth off both ends? Then you end up with what's called a standing wave that looks like this. So this is a wave that's traveling down and bouncing back, bouncing and bouncing. And waves follow what's called the principle of superposition, which you know from physics 1, vectors add together. So if you have two separate waves coming in, so here I've got this blue wave on the bottom coming in, this red wave here coming in from the right. Those will meet together and add together, and see this little red line here? That is the sum of those two waves. That's what would actually be seen at that position. Waves add together following the principle of superposition. Here's another example. So two waves on a string are coming together and meeting in the middle. What we would physically see would be this. So if I've got something bouncing back and forth, one is going this way while one is going that way. If I balance it just right, I can get those two incoming and outgoing waves to combine together in what we call constructive interference to form what looks like just a constant peak and valley here. And if I have these coming at different, so that they're out of phase, I could make them, if I try to, combine together to just completely flatten out. And we call that destructive interference. And that's one of our labs, is about interference. Okay, so if I have two different sources here, so that guy is making waves. So the way this works, this is the top view we're looking at. That bright blue places are crests and the black places are troughs. So this is bouncing up and down towards your eyeballs and away from your eyeballs. And then if I add in a second wave, those crests and troughs will combine together. So look right here at this bright blue spot. That's two crests, one from this guy and one from that guy, combining together to make an even bigger crest. At this black spot, that's a crest from the first one and a trough from the second one combining together to cancel out. Or I guess this would be a spot where that happens. And we call that destructive interference. Here they're constructing to get bigger. Here they're destructing to cancel each other out. So see, all along this line here, right through here, we're getting destructive interference. At these spots, constructive interference, where they combine to get bigger. Here at these spots, they're constructing troughs together to get even bigger troughs. That's still constructive interference. In a face-to-face class, our first lab that we do face-to-face is a standing wave lab. And the way it works is we've got a string attached to a harmonic oscillator, this little thing that bounces up and down really fast. And so that sends a wave down. This end is attached, so that wave goes down, bounces back, goes down, bounces back. And we want those to balance out perfectly so that what we end up with first, we call this our first normal mode, is the wave looks like this. So it's really waves bouncing back and forth hundreds of times. But it looks like, it appears to us, because of all the constructive interference, that you've just got this loop. And it's really bouncing up and down. And that's our first mode. And this distance here is half of a wavelength, because remember, a full wavelength looks like this, has two of these peaks in it. And that's what a guitar string does. If I bring out my guitar and I just pluck a string, that's bouncing back and forth, and you hear that. That's a standing wave. That's the whole string bouncing like this, going ooh. And so that it looks like, if you were to film this with a high-speed camera, it would just look like this. Well, if I make it bounce twice as fast, so I've got my little oscillator here going twice as fast as that was, then I can end up with a standing wave that looks like this. That has two bumps in it, two nodes, a node there and a node there. So this is a full wavelength now. So now my length hasn't changed. My wavelength now equals L. And we could get this on a guitar by using what are called harmonics. So if I grab my guitar here and I just, it's called a harmonic, put my finger right over halfway the 12th fret. Can you hear that? Hear that that's twice as that pitch? It's the same note, but an octave higher. That's the string vibrating like this. So here's the entire length of the string. The string is vibrating twice as fast as it would if I just plucked it and the whole string vibrated. And we could keep doing this. We could increase our frequency here meaning a higher pitch note, and end up with 3 notes or 4 notes or 5 notes, and those are called the harmonics. Okay, so here's a standing wave. These are our nodes. I could have 4 humps. I could have 8 humps. I can have as many humps as I want. The wavelength is twice the total length divided by the number of nodes you have. F1 is the fundamental frequency. That's the open guitar string. And every time you double the number of nodes, you double the pitch. So here I have 2 nodes. Here I have 4. This pitch would be 4 times that pitch. And that follows this formula right here. The frequency is the number of nodes you have times the fundamental frequency. Okay, now your book goes into a whole bunch of stuff with musical instruments with open ends and closed ends, and like you can learn a lot about oboes and tubas and whatnot. We're not going to go into any of that. You might have one test question about normal modes, and literally all you're doing is using this formula. But that would be it. That's all we're going to go into.